I did post the recording from Friday, and I think it's audible, but basically let me know if you're reviewing one of those and if there's something that I can do to make it clearer. But usually what I do is I try to catch most of the PowerPoint, but also I want to get the screen so that you can see if I'm like pointing to stuff. All right, let's talk about quantum mechanics. Okay, so we have a couple parts here that the thing about quantum mechanics is the question of what do atoms look like? And that's as far as we're going to get. Atkins actually has a chapter on quantum mechanics. Now, quantum mechanics is used in a weird way in this course because you can really get into the calculus. We're just going to show you the calculus on today. But we're also going to talk about how it's important for surface plasmon resonance. And you probably don't know what plasmons are, and resonance is a weird chemistry term. You know resonance from organic chemistry and all that. But down the road, we're going to be doing experiments with ViaCore, and actually at the Ericsson conference, you're all going to be talking about the proteins, and you won't be doing won't have done the SPR yet. But you will be saying we're going to use these proteins to look at SPR, and then in May you're going to actually learn how to do the SPR and stuff like that. So all that is to say, SPR involves quantum mechanics. And that's what my goal is, to give you just a taste of what quantum mechanics are for two purposes. So you can explain what SPR is, and we'll have another lecture about that. But also so you can understand why the periodic table comes from. And those are two very different things, but the periodic table actually comes from quantum mechanics in a weird kind of way. And so the thing about physics and physical chemistry, we're using physics techniques and we're combining them with chemistry. And during COVID, actually, we still had physical chemistry labs. I just made people go into their kitchens and to try out different labs. And the first lab that we did was actually a quantum mechanics lab, because it was about measuring the wavelength of light in the microwave. And by the way, microwave radiation is a form of light if you talk about the right way. So you can actually measure the speed of light. If you've ever noticed that your microwave, of course you have the hot spots and the cold spots. Those come from the fact that when the microwave is at a high, it's a hot spot. When it's at a low, it's a cold spot, because it does not deliver energy when the wave itself is close to zero. And you can actually measure the microwave. You can measure where the hot spots are in peaks. And from the length of the hot spots, you can calculate how long the microwave is. And from the length of the microwave, you can calculate the speed of light from that. So it's kind of cool. You can have all these connections between things. And the speed of light itself is a wave. But sometimes you can talk about it as a particle, like you've heard of talking about it as a photon. And it's like, which is it? Well, it's sort of both. And the thing is, electrons are the same way. It took people a long time to realize this, because of course you start off thinking that if you take something, you divide it down enough, you're going to end up with a particle. If you start off with a particle and you divide it down, you're going to end up with a particle, right? But actually, once you get down small enough, you start to see that there's significant wavelength properties. That the smaller you get, the more you get to the point where something acts like a particle in some ways, and it acts like a wave in other ways. Depends on the context, depends on how you're observing it, and it's really weird, and that's what quantum mechanics is. So the atoms at first, like John Dalton was like, atoms are just solid spheres. And then J.J. Thomson figured out there were little electrons that had to balance the positives, and so he thought it was still a particle. Then we realized that the nucleus was really small, and the electrons were moving around the nucleus. So they get this picture, and actually a lot of people's picture of electrons is probably like the planetary model. But that's actually outdated. That's that's about 100 years old, a little less than 100 years old. Because the electrons don't really move around like little orbiting planets. If they did, eventually they would run out of orbit. Eventually they would crash into the nucleus. So there's something that allows the electrons to keep moving, and that is quantum uncertainty. And so that comes from the physics equations. And so I'm going to show you a few physics equations about how electrons move if we treat them as waves. But again, we are not going to completely get into it. But if you're thinking of the atom as like this, well, this has certain usefulnesses. You can think of it this way. But this is a less accurate model, and that looks like this. And in this model, look how the density of the electron is more likely to be close to the plus. It actually makes sense at a certain level because the plus and the minus attract, and the electron is crashing into the nucleus all the time. But the electron is so small that it's partially a wave, so it never sits still at the nucleus, and it's always moving around the nucleus. And that's the main thing that I want to show you today. The lowest energy wave of the electron is just a distribution with the highest probability right next to the nucleus. So when you say quantum mechanics, actually if you look at the planetary model, you have the energy levels, and you're used to the idea that electrons can be at one energy level for that element, for that combination of pluses and minuses, and then they can't really be in between. They can hop between energy levels. That actually is a quantum mechanical idea. The idea the electrons can only be at one level or another level, but they can't really be in between. That means that they are quantized, and the planetary model actually gets that right. Technically, the quantum model is not important in that it's quantized. What's important about the quantum model is that it's uncertainty that has been applied. The uncertainty principle and wave-particle duality has been applied, which is not really applied here. But still, this is actually a very useful model. That's why people still think of it. When you see like the atomic commission and they have this kind of symbol, it's just kind of ironic to me because what most people think of as the atom, they might think of a symbol like this. But that's actually more than 100 years outdated. That's an old model that's only limited useful. So quantum just means that it's quantized in energy levels. Mechanics just means that it's moving. And like we said, the one thing about electrons, they are always moving. There's, you can like slow them down by forcing them to slow down. But in one sense, the uncertainty principle is that you can either know its exact position and you don't know how it's moving, or you can know how it's moving and you can't know its exact position. One way of interpreting that is that they're always moving, or that you don't know their position. It's that kind of thing. But mechanics is, how do we know that? It's how electrons move. And actually, classical mechanics is what you probably dealt with mostly in your physics classes. Did you talk at all about quantum mechanics in your physics classes? You mostly talked about how big things move, probably, right? Did you ever talk about quantum mechanics in any way? I just want to see if I'm building on something that you remember.
We did a little bit. I took physics for science and engineering, so we talked a little bit about that.
Okay, so they had something like this. It'd be interesting to compare how they do it, because how I do it is a ladder to get to the periodic table. And how they do it is rather different. They have different things. So, but you're used to the physics problems, like they have a car. I don't know what kind of physics experiments they're doing now, but it's always stuff you can actually touch, see, and move. Classical mechanics is typically like how the Earth goes around the sun. And that's where the planetary model came from. It actually was a classical mechanical model, but they found out that it didn't really work for the thing that was that small. How an electron goes around a proton, at first they thought maybe it's like how the Earth goes around the sun. But soon they found there were problems with it, including that a planet can fall into the sun and stop moving, but the electron cannot, because the uncertainty principle prevents that. So the other thing is that electrons have wavelengths, and technically every piece of matter has a wavelength. If you can describe something as a discrete particle or a discrete object, you can calculate its wavelength. So you have a wavelength. It's just that you're very big relative to the wavelength, and it's incredibly small. I don't think it's even possible to measure it. Electrons are small enough. The smaller you get, the bigger the wavelength gets. And so electrons are small enough that the wavelength is actually something that matters. And light, in a sense, is so small that the wavelength is almost all there is, unless you want to talk about it as a photon. So it's kind of interesting to get into this. And so there's going to be some things, because I'm not proving stuff, I'm not interested in proving this to you today, that it would take a whole class to do that. And in fact, we have a whole quantum mechanics class that you're welcome to take. But I'm not sure I have the math prereqs for it. You know, Schofield would probably say, oh, you have to take some more math before you take my class. But quantum mechanics, it does have a strict logic, and it does come from mathematical equations. So just because we aren't going through all the mathematical equations, know that they're there. And they are forcing, you know, there's nobody who's sort of a quantum mechanical heretic when it comes to the equations. Everyone agrees on the equations. The thing people don't agree on is what they mean. And so as a Christian, I look at the Trinity, and I think about the thing about the Trinity is it's not really it's not reasonable. You can't divide it up and have the exact rationality of it. It's not ratioable. And here's a quote about the Trinity that is talks about quantum mechanics. So McGrath actually studied for a PhD in science. I think he got a PhD in science, and then he went into theology. And he said that what I studied in quantum mechanics was kind of like the Trinity. The quantum mechanics and Christian theology, they are perfectly rational. It's just you can't take a ratio of it. Their logic seems counterintuitive if you judge it by common sense. Our common sense is set up to deal with our scale of things. And our scale of quantum mechanics is not on our scale. So we kind of have to follow the equations to see where quantum mechanics gets to. So there are going to be some things that are non-commonsensical. And like I said, the equations everyone agrees on, but what the equations mean are a real case of disagreement. This is a question of, if you look at the interpretations of quantum mechanics page, you can actually get all these things, and you can see some of the names from previous slides that you have. You have the question of what they mean, and you have all these different meaning questions. What does it mean that the wave function is an equation, but is it real? No, yes, agnostic, I'm not sure. Yes, no. You know, all these different people. And it's funny because you go to the Wikipedia page for different denominations of a religion, and you can see similar kinds of things. There are things that everyone does actually agree on, but then there's different sort of denominations, and science is not immune to this. You have the different sort of interpretations of quantum mechanics are kind of like the different denominations of the faith. And there's some fascinating things about how it all gets into. But again, this is physics, okay? We are sort of dipping into this to sort of understand one thing that you want to know. The crucial insight is that everything can be seen as a wave or a particle. Okay? Quantum mechanics means, and waves are fundamentally quantized. That's the thing about waves. They go up and down, and you have to wait until it comes back to have a complete wave. Waves are fundamentally quantized, and quantum mechanics says that everything has a wave to it. So you can think about, like I said, the higher energy level idea is actually a quantized idea, but you can turn it on its head. Every particle, a wave can be seen as a particle. This is photons, and you talk about light as a photon, but also, depending on the thing, you talk about light as a wavelength, right? As a wave. Well, what's waving? You know, have you ever asked that question? They actually asked that question, and science went down a wrong road for a long time because they said the ether is what's waving. But we don't teach that to you because it's not real, it's not true. There's the what's waving is the light itself. And so, what does it mean? Well, we have to think about what if I'm saying it's about the equations, let's talk about the equation. It's a pretty simple equation. The wavelength of anything is inversely proportional to its momentum, mv. The other thing about this is that light has a constant velocity, and actually light has a momentum, but it doesn't really have a mass, it has a constant velocity. So This applies to light as well, but it's a little bit weird how it applies to light. But anything that has a mass and a velocity as well can be thought of as having a wavelength. That's why, and by the way, when I said that you have your wavelength, it actually depends on what speed you're going as to what your wavelength is. So if you go faster, now it doesn't, like I said, these are vanishingly small. It's questionable whether I should even be talking about this. But it's mathematically true that you have a wavelength that is dependent on your momentum. When your momentum changes, your wavelength will change as well. So something very big, and if it's inversely proportional, something very big has a big M. Something moving very fast has a very short wavelength, but something very small has a very big wavelength, which means that we can see it. So I'm going to refer to this at the beginning of all the data talks, by the way. And so this is not actually a data talk, but we're going to introduce those. And so I want to say that there was a singularity, there was a beginning to the universe, which wasn't always obvious. There were a lot of people that were like, the universe has no beginning and no end. Well, and maybe, and there's other people, and this doesn't solve it, right? Because there could be something before the beginning. But there's something that looks an awful lot like what we would call a beginning to the universe. And the first thing that happened is light. You actually had dark ages for a short time before you even had atoms and stuff like that. But the first thing to sort of emerge after creation was light. So I just find it kind of funny that in the beginning there was light is actually a pretty good statement about creation. The light condensed into matter, the light separated into, and this is one where you get to modern scientific terms, separated into protons, neutrons, and electrons. And one of the things about the universe, the plus things are very heavy, the minus things are very light. To get a neutral atom, you have to get the plus things and the minus things together. And they do attract each other until you get to a neutral plus and minus charges attract. So the protons attracted the electrons, and in a sense they constrained them, they tied them down. If you have a proton and an electron flying by, the electron can go anywhere at once, but once it falls into the energy well of the proton, it starts to be constrained by the fact that the proton is attracting it by the force. And the plus-minus force is actually calculatable in some situations from the physics equations of plus-minus forces that we develop for, like, static charged spheres, if you've done that in physics. I did ask, and I think that you occasionally did deal with charges in physics, the Q1, Q2 over R equation. Actually, from that, we can actually build up how to talk about a protein. So those things do work. So what we're going to do is, but the thing is, electrons are so light that they can be described as waves like we describe light waves. You can talk about electron waves. You cannot precisely measure both electron position and momentum at the same time. And so the particle, when you get down to its wavelength, which is about the size of an atom, the particle is spread through space like a wave. So if we want to say what is an atom like, well, it's got a proton, which doesn't have much wave character, it's more like a particle. But then you have the little light electron that is more like a wave. So every atom is actually showing wave-particle duality in the sense that when you get down to it, electrons are waves until they're not, until you look at them another way. So because we can see the electron, we can calculate where the electron wave is, and we can calculate where it will be most stable. If we have a plus charged proton and a minus charged electron, we can calculate that the QQ force is going to be attractive, so the electron will move over to the proton, and the best place for it to be will be sitting right on top of the proton. And this is exactly what quantum mechanics says. The only wrinkle is the electron doesn't stay there. But the most stable place for an electron to be is right on top of the proton. So the wave of the proton, where you calculate where a wave is, you take a wave function which describes the wave, and you have to square the wave function to talk about position. So wave math is weird. And we don't have a prerequisite in wave math for this class. But the wave function, you take the square of it to find the position. So I trust them on that, you can trust me on that. Now the other thing is that we're, technically electrons are in 3 dimensions, right? So it's a 3-dimensional wave. Really complex, but we will explain it with 1-dimensional waves. So this is what a wave function looks like in 1 dimension. You have the wave, the psi is the wave function itself, but the psi is a wave, because it's a wave, it has a positive and negative part, right? Well, that doesn't make sense. You can't have a negative position. You know, your position is, you can't have a negative existence, basically. The electron is always, it's either there or it's not. So it doesn't make sense to say the electron is negative there. Position is a simple number. And so to go from a wave, which can be positive or negative, to a position, which can only be positive in that sense, or 0, you have to square it. But that's actually pretty easy to do. You just take the wave and you square it and you find its position. If you have the wave like psi right there, and you square the wave, you can imagine what happens is that the shape of the wave changes a little bit, but the big thing that happens is that the negative part of the wave becomes positive. And you can say, if you have this wave, okay, what is the chances that the wave is a probability that something will be at that certain place? The wave will never the wave will never be active at 0. When the wave is 0, there's nothing there. Okay? And you see the wave is 0 at 3 points. See the 3 points? Wave is 0 here, the wave is 0 there, and where else is the wave 0? Right where it crosses the axis. Wherever the wave is 0, if you take the square of 0, you end up with 0, right? So where the wave is 0, there's a node, which means that the electron, or whatever is represented by the wave, can never be at that exact location. We've constrained it by saying the wave is a line that runs from point 0 to point x, whatever this is. So we've constrained it to be 0 at the ends of it, but the fact that it's a wave also means that it's 0 in the middle. So wherever there is a 0 part of the wave, you will never see the electron there. Other than that, you can also say the probability. You're more probable to see the electron. You're more likely to catch the electron at the top of this, but you can sometimes catch it over here or over there. This is the probability of the location. Psi squared is the squared wave function. And actually, it works out to be an integral form. And so if you remember, integrals are always going to have the function times the small little section, the dv, the little slice of it. And so the probability of finding a particle in volume dv is actually the wave function squared times dv. And then you actually integrate that. So you actually do that. It's just you're doing it with wave math in 3 dimensions. But it's the same kind of calculus that we do with 1-dimensional stuff. So this describes where a wave particle will be. It's always probably it will be there or there. But you can also say it will never be in a certain place. You can't be sure where it is, but you can be sure where it isn't. Okay? And that is where I have this. So I actually haven't used this since COVID, but I was very happy to find out that if the batteries like burst and stuff like that. But this is a wave machine. So I think you all can see this if I do this. Okay, so it's just a string, and the string doesn't have any energy in it. It's not really a wave right now. But I'm going to turn it on. Okay. So if I turn it on, okay, I can even hold it like this. So it has the LEDs, and so you can see the different, you can see where the wave is. We put the energy in, oh yeah. But you put the energy in, and you see it going like that. And I can actually turn the speed of it up and down, although honestly it doesn't give me a great range. I can try, see, this is the flashing speed. I'm not even quite sure how I should be doing this. Okay. So now you can see hopefully you can see there's 3 nodes, and I'm going to, the motor's at the maximum right now. But you can see that this wave actually has 3 lobes, and there are 2 nodes like right there, where you can never, where you're at 0. If you take this and you square it, then you still get 0 there. Let me play with the motor speed. I'm going to turn down the motor speed, see what happens. And you see now we no longer have a stable wave, like sometimes we don't have a stable wave. For a brief instant, you can see sometimes we can get like more nodes. If you look very carefully, like right there, you see that there's like 5 nodes, although it's kind of hard to get 5 nodes. There was like 4 for a second. The 3 is the easiest one to get. And actually, if I change the length, watch this. There. You see that? That's it's a little lopsided, but it's sort of 2 node. It's sort of like the picture that I was showing on the thing a second ago. Now the other thing I want to do is I want to get back to here, and then it has a demo setting. So I'm going to see what the demo setting does is it changes the speed. So you can sort of see there it has a 3. And there it is, changing the speed. And you see how when it changes the speed, there are places where it's not a stable wave. And so you actually, it doesn't meet the proper conditions. If the wave's not stable, you won't see it you won't see it as a ordered wave at that point. And so this wave is quantized. You can get 3, you can get 2, you can get 4, but right here is undefined. This is not a standing wave. And so there's only certain, this shows you why waves have to be quantized, not quantized, and then you have the place where it's quantized. There we go. And here we have the 2 that I was able to get. But you can talk about the exact length of the different things there. So electrons, in a sense, are like standing waves. And the other thing is that what you do when you have the air coming through here, the air sets up a standing wave depending on its length. And the one thing is, where is the other one that we have? I want to do both of them at once. Because if you listen carefully, there's only a very slight difference between them, because I think this material is actually stretchier. And so the length ends up being slightly different. But my left, you hear how that note, the lowest note, is similar to that lowest note. The length is what's determining the note. And try as I might, standing wave here. As I put more, there's going to be more nodes in that standing wave. We can't see them. And if we get Vinny's note, it's hard to do that. But that one has even more nodes because you're putting more energy into it. It's waving more. But it's still constrained to be the same length. The length of this is not changing, except when I possibly, if you listen to this, if you listen to it carefully, I think it's slightly different tuned. Again, I think that's because its length is very slightly different. So you can play like the Superman theme. Do you guys? Okay, so do you hear it? So John Williams wrote the Superman theme to have very simple harmonics, and those are the simplest ones to get. Like if we just spin it really fast, we would start to get higher and higher notes. But we can't get in-between notes with those. To get the in-between notes, we'd have to have a different length, a different standing wave. And so, because it's quantized, and that's why pipe organs don't have just one pipe. You know, with horns, you can change the length by using the valves and stuff like that. With pipe organs, you have one pipe for each note. And because you have one length for each note. So, that's the cool thing about waves. You can do it with Christmas lights if you want to. And again, so the main thing is more energy gets put in, the wave gets more nodes. And the wave, you see that the amplitude doesn't change that much, but the wavelength is what's really changing here. So if we're talking about anything that's a wave, however it's constrained, if it's constrained to a certain dimension, and a one-dimensional case for the wave, is we have certain energies where that wave can exist. If it's constrained to be tied down, if it must be zero, at 0 and L, at the ends of the box, it's like it's like the string. The string is held, so it must be 0 at the ends of it. We can put more energy in and get more zeros, and so it actually will be at higher energy, and it will have more nodes. But it's always going to be tied down at the ends, because it has to be a wave. If it's not tied down at the ends, it's not a wave, and it doesn't exist. So that's why we have this idea that we have a particle in a box, one-dimensional box, must be tied down at the ends, add more energy, get more waves and more nodes. You always have nodes at the ends of the box. It's always, the potential is 0. So you can think of this, it's like this is a one-dimensional representation of an electron. And this is why we say the energy is up. The electron actually isn't in a different place, but it's at a higher energy, and it can do more things. It might be, it has more energy, it has more nodes. In a sense, the electron is not necessarily farther out, but it has more places where it can't be. And these electrons also can do more things chemically. So this is like a piano strings, it's like a pipe organ's pipes, and because music is quantized, there's actually interesting connections between music and physics. But we don't have enough time to talk about the physics. We just have enough time to talk about them. We definitely don't have enough time to talk about the music too much. But if you want to get into it, there's a whole literature. Okay, so that shows how waves are quantized. Only 4 notes can be made, and I see in the literature they say 5 notes can be made, but they must be able to swing it really fast because I don't trust myself enough. I wouldn't want it to fly out the window or something like that. But these are simple overtones, and the way that wind instruments work, the easiest notes to get are what we hear as our major scale. And it's interesting that music is very different across the world, but the idea that these notes are the easiest ones to hear, they're also the easiest ones to make. So there's freedom in music, but there's also some constraints in music. So standing waves constrained to the pipe must be quantized. And so that is actually related to this equation. Now I want to show you an actual wave equation here. This is actually, this equation looks weird, but it takes a wave and it tells you what the energy of that wave is. See, energy times wave function. The energy of the wave function equals potential energy times plus kinetic energy. That actually makes sense from the physics that you're used to. And if you look at kinetic energy, what about this? Do you see that something similar to the kinetic energy, 1/2 mv squared? If you think about 1/2 mv squared, what do you see that's similar? So this is actually a version of 1/2 mv squared for a wave. And there's 3 things that are kind of similar. Can you find one of them? What is v if you take it down? What is velocity?
Meters over, or distance over time.
Right, meters over seconds. Now we don't have speed as a meters over time, but we do have x, which is a distance. So distance over time on x. Here's where the velocity squared is. And by the way, this is divided by it. You see how the x is on the bottom rather than on the top? Well, then there's the m. So there's mv squared. And instead of 1/2, it has all these weird constants, which has to do with proportionalities of very small things. But they are constants, just like 1/2 is a constant. So you actually have 1/2 mv squared shown here. It's just on the bottom rather than on the top. But it does help you to see there's a little bit of kinetic energy is a second derivative, just like acceleration is a second derivative of position changing with time. So you actually have, technically v is dx dt, Oh, and by the way, you have dt right here. Time is sort of weird. It's all weird, but I want you to see the square, basically. The v is squared, just like the x is squared right here. And so kinetic energy is actually the same at these different levels. It's just that you're applying it to something that can be a wave rather than something that is a particle with a defined location, you know. So we've got to simplify this. And, you know, even this, when scientists look at this, actually, like, what's the potential energy? This is where they start. But this is too hard for them to calculate. You have to introduce boundary conditions. But we do know that there are some boundary conditions. Protons are a certain mass and charge. Electrons are a certain mass and charge. And the electron is tied down by the proton. So just like we had the particle in the box that was tied down at the ends, in three-dimensional space, the proton is tying down the electron and is making a constraint. And we also have to have the three-dimensional wave must fit into the three-dimensional box, in the sense that our one-dimensional wave have to fit in the one-dimensional box. It's a little bit weird, but it's kind of like the wave has to meet itself. It's not really a wave unless it returns to itself and makes a complete wave, like, you know, the infinity sign is even something like that. So the ends of the wave have to tie together in 3 dimensions, and it's like a boundary condition, but it's a mathematical thing. So all this is, I want you to realize that this really is just carrying out physics equations of using mass and using wave math, which we don't teach except for quantum mechanics. If you're using very small things, you need to know wave math. Most other people don't need to know wave math. One way that you can demonstrate sort of wave math is that has anyone ever played with a spirograph? So it's kind of like a gear, and you put your thing in it and it makes these patterns, right? Well, if you do the spirograph, what you usually do is you're actually doing a kind of 2-dimensional wave. And if you look at where this 2-dimensional wave works out, the biggest density of lines is very close to the center. So if this is like an electron, you can think of the electron wave as kind of like this. The biggest density is actually very close to the center of the proton, because the plus and the minus are attractive. This is one of the things, you know, I actually, when I learned this in physical chemistry, it was different than what I expected. So that's why I'm harping on it, you know. But the idea is the electrons are actually drawn to the protons. And so you don't have to make it more complicated than that. It's most probable to find them close to the electrons, especially if they have the lowest energy level, the simplest wave with the least nodes. So here is where I'm going to hope that this works. This is I'm going to give you a few examples of 2-dimensional waves. That's the one thing I didn't check. Here it is. Well, we'll see if this will actually run it. There you go. Okay, so see if you can try to imagine what this guy's going to do. And I think you can hear the sound. So he's just putting sand on a 2-dimensional table, but it is circular. The boundaries are the edge of the table. The sand shows you the probability of the particle being there. He brushes the edges, right? It doesn't make the best music, you know? Kind of experimental music. But you see that the particles start to gather in one place. And there's a small probability that they won't be, but there's a high probability that they'll be located in those lines. And it's constrained by the shape of the table. The waves in the table set up the waves of the particles, where there's resonance, where there's like a high amplitude. And so now he's applying another wave to the table. And look what happens to so another form of delivering energy, he's applying another wave. I don't know if it's higher or lower energy, but it's definitely different. And you see that it sets up a different wave in 2 dimensions. And now he's using another one. You can also hear it makes another wave. Somebody's saying it's like a bell, and there's actually like singing bowls. There's a Chinese singing bowl expect them to be and places where they will not be. So that's what you can do. So, have you all seen Jurassic Park? The first one. There's a famous scene where they have the cup of water on the dashboard, and the T-Rex is coming, but you don't see it yet. You just feel it. So of course they have the sound, but they also, you see the wave of the two-dimensional wave of the impact. By the way, you know how they did that? They actually set up a string inside the dashboard, and they plugged the string. And the string set up a two-dimensional wave. So you can actually do things, like if you have more complex notes, of course water is going to be, the surface of the water is a two-dimensional wave. And you can actually see, if you have high-speed photography, you can see that the different piano notes set up a very rich number of waves. But they're standing wave patterns. We can talk about where it is and where it's not, even if it's very complex. And by the way, these are the different notes. So like this is C1 sharp, what it does in a, you see they have different nodes. You see these dark spaces are the nodes where the waves are zero. And they even have used these in chemistry. So like they will set up a liquid template, and instead of like putting everything in place with tiny tweezers, which is not possible in chemistry most of the time, what they do is they use the standing wave to set up the pattern. So like you have things floating on the wave, you apply sound to it so that it will make a 2D pattern, and depending on the sound, it will make different patterns. And then you do chemistry that sort of makes all the little spheres fuse together. And then you froze it, that exact thing. So this is the ideas of what they've done. Different waves will make these different shapes. It looks like the sand, but this is just on a microscopic level. And if you change the edges, you also get different patterns. You see how these, I believe these are the same sound with different patterns in it. And so you can actually arrange things without having to directly contact them by using the sound wave to constrain the reaction. And one final thing about waves, there's an artist who actually went through and took pictures of waves. And you see how the waves can actually, they can constructively or destructively interfere. And by the way, waves constructively interfering, an electron being attracted to two nuclei at once, is the basis of chemical bonding. But there you're having two electrons, there you're getting really complicated. But the idea that bonding is a little bit like this, in that you have the electrons located between two nuclei. That's actually a completely accurate picture of bonding. And actually, no matter where you go, if you talk about this to somebody who knows their chemistry, they will be impressed. You don't have to prove it to them with electrons. You just have to talk about it right. And that's one of the reasons why I want you to talk about it right on tests. So here's just another thing, and you can see the waves propagating. You can see the nodes as well as the peaks as well as the troughs, basically. And you can get some really cool patterns if you just constrain the wave in a certain way. The proton is the constraint on the atom. Okay. So that leads to the second one. And I do actually